Ladies and gentlemen, I welcome you on our today's EnerGizerS special session. My name is Wziął. I'm working at AGH University of Science and Technology in Krakow. And I have the pleasure to be a project manager of this Polish-Norwegian project. First of all, I would like to say a few words about our project. The full name of the project is CO2 Enhanced Geothermal Systems for Climate Neutral Energy Supply. This project has received funding as part of the 2019 Polish-Norwegian Research Project, financed under Norway grants via the National Center for Research and Development. Our project is realized by Polish Norwegian Consortium. AGH is project promoter and Mineral and Energy Economy Research Institute of Polish Academy of Science from Krakow is our Polish partner, and also Exergon company from Gliwice is our Polish partner. From Norway, we cooperate with Sintef Energy, as well as Norwegian University of Science and Technology. The project started in 2020 and will last till 2033. So now we are more than half of the project. So today you cannot find our final results, but we would like to say information about work which have been done to this project and plans for future. The main objective of the EnerGizerS project is to progress the technology of enhanced geothermal system using carbon dioxide as a working fluid, and we would like to analyze test fields. This test fields located in Poland and in Norway. In Poland, we find 2 places, and in Norway, we selected 1 place where our analysis will be done. A very important aspect of our project, as well as other Polish-Norwegian projects, is cooperation between partners, between Polish and Norwegian parties. But let me start from the beginning. I would like to say a few words about technology which we would like to develop. It's enhanced geothermal system technology, technology which allow extract energy from hot dry rocks, dry or almost dry, when hydrothermal system is not possible to use. It's unlike hydrogeothermal system. It's zones when reservoir is without water, and it's possible to extract energy by artificially increasing the hydraulic capacity of geothermal reservoir. Then working fluid is introduced to the reservoir, and this working fluid, mostly it's water in EGS project. This is medium which can bring energy to power plant, combined heat and power plant. In the world, it's not new technology, because it's technology developed since 70s, last decade. The first installation, which is installation was created in the United States in Los Alamos laboratory. And from these times, several projects are developed on the world. Here you can see location of selected enhanced geothermal systems. As I said before, the first was in USA, but recently the new demonstration system was developed also in China. From our point of view, the Ogachi system, which is located here in Japan, is really interesting because it's only one in the world which use carbon dioxide as medium, as working fluid. Other systems using water. Water is most common fluid in all enhanced geothermal system in Europe. Till now in Poland, it's no enhanced geothermal system. Probably you know, in Poland we're using only a hydrogeothermal system. In Poland we have 6 geothermal heating plants using water from geothermal reservoir. But till now we have no enhanced geothermal system in practice. But from 2010 we started scientific research to finding the best place to do first pilot EGS system. And our work showed that in Poland it's possible to do it. We find a few locations in different kinds of rocks. The first one you can see here on this map. It's pink color, its location for enhanced geothermal system in volcanic rocks. This green one is possibly place located in sedimentary rock, and the last one is also place when EGS system was functioning in crystalline rock. This work was done in case of enhanced geothermal system which was using water as working medium. And it also was based for our work which we do in EnerGizerS project. Our project joined together 2 purposes. The first is energetic purpose. We are looking at the best place and the best solution for producing energy from dry rocks. But the second one is CO2 sequestration. Some part of CO2 will be injected to the reservoir, will remain in the reservoir. We assess that it will be about 5–10%. We will finding in our final modeling. So it's the second purpose of our analysis to find the best place and best solution to do it. First of all, we are looking for energetic purpose to produce energy, electricity and heat. And second purpose is looking for possible place to CO2 sequestration. In classic geothermal system, we are looking place where permeability is high. It's and this natural permeability which guarantee that water will be in reservoir. In EGS, we are looking for systems for reservoir where permeability is really low. In CO2 EGS system, we combine this requirement, and you can find here the system or reservoir is characterized by low permeability, but not so low like in classic geothermal enhanced geothermal system, because some part of carbon dioxide will remain in the reservoir for CO2 sequestration. As I mentioned, we are here in our project, so it's a lot of time to finish it. We started 2020, and now it's more than half of the project. And we finished 2 work packages. The first one, it was identification of key parameters for effective use of the CO2 EGS systems and selection of appropriate location. It was really important work package because we choose the location when we will do next analysis. It was possible because of development of criteria for selections, optimal location, as well as detailed geological analysis for looking this proper locations. You can see here 4 tasks which we realized to find these locations. And finally, we finding 2 locations in Poland and 1 location in Norway. Our next presentation will be connected with detail how we choose this location, but I can say that the matrix of influence method will be equipment which allow us to find this location. In Poland, it's Gorzów block and Górniczo-Hutnicza area, and in Norway, it's Are formation. What is important, we're looking also similarity to other enhanced geothermal system project. And very important project for us is Górniczo-Hutnicza project, because it's project located near Polish border, near Berlin. It's I think similar project to this one, which could be good functioning in Poland. So it was some case we were looking for. Work package 2 is also finished. It's a work package connected with detailed analysis on laboratory test. This test was carried out in EnerGizerS laboratory. And for a second, I will have a pleasure to show you more detail about this. We carried out analysis of mineral composition of rock and pore space, as well as thermal and mechanical analysis of properties of potential reservoir rocks. Here you can see our core sampler prepared for our further laboratory tests. The work packages are on progress. Work package 3 is connected with experimental determination of properties and behavior on CO2 EGS working fluid. As I mentioned before, carbon dioxide is an attractive medium in such kind of installation, and you would like to know the parameters. So we prepare some experimental campaign. Our partners from Norway, Sintef, is the leader of this task, and the analyses are carried out in the laboratories. Very important part of this analysis are our cooperation with Polish-Norwegian partner. Part of from this cooperation is 6-month internship of PhD student of EnerGizerS, Maciek Szymanek. Maciek is present with us, and today he say a few words about the stay in Norway. Work package 4 is led by Polish Academy of Science, by Maciek Miecznik. It's connected with mathematical modeling of geological reservoir for CO2 EGS exploitation, but EGS has a lot of contribution for this work package also, because we prepare structural parametric modeling as well as modeling of fracturing process. Here you can see some parts of our works. It was done in Petrel software. Work package 5 is connected with mathematical modeling for CO2 based topside system for heat and power production. Pre-task was defined here. Topside concept design is developed for each investigated scenario based on input from other work packages, comprising extraction states and flow rates, as well as the injection states. Also in this work package, system and component will be modeling, and we perform also simulation and optimization of the system. The last work package is connected with techno-economic and environmental aspects. I think that it's really interesting for us because everybody wants to know how many it costs and what will be the impact of our environment. We just started this work package, but at the end of the project, I hope we will know such parameters. And because based on the technical parameters from mathematical modeling, based from other work packages, the costs of CAPEX and OPEX and cosmetic will be analyzed. And for techno-economics, pre-feasibility study will be performed. Also based on the thermodynamic parameters, the ecological effect will be assessed and analyzed. And the last task is connected with regulatory and policy frameworks analyzed. And today I would like to welcome you for our session. I just start the session, talk short overview of this our EnerGizerS project. Here you can find our schedule for today's meeting. After my introduction, Leszek Pajek, which is coordinator of work package 1, show result from finished work package, identification of key parameters of the effective use of enhanced geothermal system using carbon dioxides and selection of appropriate location. After that, I will back here and show you results from our laboratory test. Maciej Szymanek, our PhD student, say a few words about experimental determination of properties and behavior of carbon dioxide as working fluid. Mathematical modeling of geological reservoir will be introduced by Maciej Miecznik, and Paweł Gładysz show us framework of mathematical modeling of CO2-based topside system for heat and power production, as well as techno-economic and environmental assessment. So please enjoy our session. If you have any question, we are open to discuss it.
Hello, everybody. My name is Leszek Pajek, and I'm going to briefly show you the first stage of our project. That's the identification of parameters important for EGS CO2 system. So I would rather focus on the methodology, how important variables, important parameters were indicated. And that's the target of our work, of course, in this work package. So the target of the project itself is to analyze efficiency of EGS CO2 systems. So that's EGS systems, enhanced geothermal systems operating based on CO2 as working fluid, and try to estimate how they interfere into our environment. When we are talking about this stage of the work I'm going to introduce you today, that's identification of factors of variables relevant to selection of the location such a system, identification and discussion under those factors, and identification interconnection between those factors, technical qualitative risk assessment, and the work I'm going to introduce you today, based off published already paper. You may find the QR code in the slide. You may enter it. You may download it. That's open access paper. So in this stage of the work, you are using cross-impact method. This method is widely used in foresight works. So that's method able to indicate parameters important for developing on such unknown processes, unknown installations. So unknown, that means not exactly in technical scale reliable what's going on inside. And this method based of studies when the group of experts cooperate by certain scenario. This scenario I'm going to introduce you. And finally, in the surveys, when we have dependence of parameters and influence to the other, we are able to indicate some key factors. Key factors, as you can see, that's the factor highly dependent on the other and highly influenced to the other factors. We are able to indicate targets. Targets are highly dependent on the others, but its influence, it's moderate. Results, that's the factor, highly dependent on the other, but the influence of other factors are very slight or significant. And we can indicate determinators, regulating factors, auxiliary factors, autonomous factors, and external factors. All of those factors are important because they have slightly different meaning when we are talking about the system in general, in the whole. So the method itself based of judgment of group of experts. And our work was divided within, as I remember correctly, for 9 stages. I'm going to briefly introduce you. So the first stage, that was the problem formulation, goals and survey definition. So you can see that targets indicated here. So answer we were looking for, that's how to different factors influence the CO2 EGS location and operation. What are key regulating, auxiliary, external, and autonomous factors? And finally, what are targets, results, and determinants? So the second stage was the process when we have chosen the group of experts. That was 20 experts, 12 experts from the Polish side, and 8 experts from Norwegian side. All of experts was representing or were representing different fields of skills, knowledge. So we had people who were the experts from geology, reservoir engineering, process engineering, environmental impact assessment, legal aspects, economics, safe and risk assessment, and most of our experts declared the expertise level in more than one field. The third stage was the definition of important variables. That was the preliminary stage when all experts or each expert was able to suggest some variables, factors important from their point of view to the process. After that, we were trying to reduce the number of variables, the numbers of factors, to reduce the time for preparing the final result. And stage 5, that was the final approvement of the final list of variables. After that, Anna already mentioned about the matrix of influences. And after that, each expert were filled the matrix of influences. How the matrix of influences looks like, I will show you on the next slide. And filling that matrix, that was the last stage of the work when our experts were involved. And that's the example of the first 10 factors important and indicated by expert and approved finally as important according to their knowledge. So we can see that each factor has the number, long label, short label. By using short label, we might say that's the contraction or acronym of the label. And after that, we had label description and FEM when the label might be located. So there was environmental, technical, economical, law factors, and so on. And that's the example of the part of matrix influences. So you can see that we put all variables on the row of the matrix and column of the matrix. And after that, the role of the expert was to feel how each variable influenced the others. And of course, there was the rule that 0, it was no influence, 1, weak influence, 2, moderate influence, 3, strong influence. And after that, that data were processed by using some methodology and software. That's the open source, or maybe not open source, but free to use software you may download from the Lipsor website. That's called MICMAC method. And finally, we receive the location of any variable located on the surface of influence and dependence. So based on the methodology, the cross-impact method, we were able to link them to key factors, targets, results, and so on. So those factors I mentioned to you in the beginning of my presentation. And the method itself is able also to indicate the influence between variables. And that's the example how the strength of influence of variables might be present. So we can see that variable 3 is highly dependent on variable 2 and variable 39. There is the number of variable and a long label of this variable. So we can see that that's obvious that air quality, that's variable 3, it depends strongly because 3, that's the strong influence from the current primary energy carrier used in analyzed area, and it depends on degree of urbanization in this area. And when we go to summary, I think one of the most important information we received, that's in the group of determinators, motors, and brakes, we indicate the technology offshore and onshore itself. So the technology onshore were indicated in Polish case, and the offshore technology was indicated as the key technology for Norwegian side. In the group of auxiliary factors, that's factors we can partly control, for example, by choosing the location. That's formal constraints, availability of CO2 sources, geological recognition level, and the distance from CO2 EGS system to the electricity grid. As external factors, that's factors influence strongly, but we cannot control them, or the control is limited. So external factors is located here, where indicated existing wells and other infrastructure. That label was important, especially when we are talking about the level of recognition from the geological point of view. Depth of EGS system, water depth, that's of course important in case of offshore systems, physical parameters of reservoir rocks and reservoir parameters. Key factors are located here, so it's highly dependent from the other, but also it has high level of influence to the other variables. That's level of the technological readiness of the technology when we are talking about technology EGS CO2, and long-term safety when we are talking about results. That's parameters located here. That's cost of drilling and fracturing, cost of energy obtained by the CO2 EGS system, local regulations on the utilization of geothermal energy, local regulations of CO2, and social acceptance of CO2 EGS systems. Final summary. The most essential variables for the development of EGS CO2 systems technology selected here in this stage of our work. That's formal constraints related to local nature protected areas, availability of CO2 sources, level of geological recognition, the distance of the system to the electricity grid, and as existing wells and other infrastructures, depth of EGS systems, water depth when we are talking about offshore technology, physical parameters of the reservoir rock and reservoir temperature. Thank you. Maybe would you like to ask about something? From my daily work, I'm the engineer, and I like that method because it's able to make or to give qualitative information from the very, let's say, strange or untypical work done by a group of experts.
Let me ask you.
Yes.
Why do you use carbon dioxide instead of water as a working fluid?
Okay. I will try to answer your question. It isn't related to this stage of it isn't the question to my presentation in general, but thank you for your question. From my point of view, my colleagues may add something. We are trying to find or to use CO2 as working fluid instead of water because it has lower viscosity, so it's easier to pass it through the reservoir. It gives lower resistivity, and of course, by using CO2 and partially sequestrated in the reservoir, we receive energy and negative emission.
What's the purity of carbon dioxide that you use?
It's technically pure carbon dioxide.
99.9.
Something like that. That's quality you are able to use in any technical solutions. including CO2 sequestration.
I may supplement my colleague.
I would like to supplement my colleague with answer. There are also other factors favoring CO2 because we are talking about supercritical CO2. And the other factors are also the buoyancy force because unlike water, the supercritical CO2 exhibits a big change of density with pressure. And when we inject CO2 with a deep well, it gets denser and denser, but when we extract it through the production well, it expands, and it expands, it changes, it makes its density lower, and we obtain a so-called effect of thermosiphon, which means that at the injection well, we inject it with a higher pressure than we get it from the production well at the wellhead, at the surface, which means that there is a constant circulation without circulation pumps. And this additional effect that is very satisfactory to us because we don't need to spend energy for circulation. That's another advantage. So we can inject more CO2. It has less heat capacity, but we can prove that as it is less viscous, we can inject more CO2. The flow rate is higher, and we can extract around the same amount of energy from the reservoir rocks, but we do not need to spend energy on circulation pumps.
And maybe I add something. When you create the artificial reservoir, when we are talking about EGS systems, we are going to create permeability, which is not in natural state. So the key is to be able to use the whole volume of fractured zone. And when CO2 has lower viscosity, it's easier to them to flow to the side part of fractured zone.
Thank you, Leszek, for your presentation. I think CO2 behavior will be also subject of our next presentation. Now I would like to say a few words about characteristics of the geothermal reservoir based on the results of comprehensive laboratory test of rocks. This test was done in AGH on our laboratory. As Leszek said in previous presentation, we choose location for our survey. We choose also method for selecting this best location, matrix of influence, and finally we find two best location in Poland. The first one is here, is Gorzów block. And I can say that it's our first location, and second location is here. It's onshore, opposite to Norway selection, because in Norway we find first of all other formation, but our Norwegian partners also find two more formation. Is here on North Sea, Skagerrak and Ula formation, but first of all, this other formation is interesting for us. Take into consideration, we prepare some geological analysis for this location. We know that in Gorzów area, the reservoir rocks are sandstones and also effusive rocks. And these effusive rocks are really interesting for us. Reservoir depth should be probably depth about 4,200, 300 meters, and the temperature will be there near about 150 Celsius degree. In other location, in Kutno, Kruśniewice-Kutno area, reservoir is deeper. There is also sandstones, but this sandstones of lower Triassic reservoir. And because of the deeper reservoir, the temperature is also higher. It's between 165 and 195 Celsius degree. And other geological conditions are connected with other formation, this offshore formation selected by our longitude region partner. The reservoir temperature is near 160 Celsius degree. And there is also sedimentary rock, mostly sandstone. For this location, first of all, we collect data. This data are connected with core sampler, but we started from collected archival data to know some petrophysical and mechanical parameters. After that, we collect total 52 core samplers. 42 core samplers were collected from Ośno IG2 borehole. It's a borehole located on Gorzów Blogaria. This is our first location. From interval about 3,200–600 meters. 10 core samples were collected from Mesozoic reservoir formations, from Are, Skagerrak and Ula offshore formations. These core samples were tested in our laboratory to do petrophysical characteristic of the geothermal reservoir. We perform petrophysical, mechanical, thermal, and mineralogical tests. In case of petrophysical analysis, we measurement pore space saturation by nuclear and magnetic resonance method, as well as pore space investigation using the mercury porosimetry method. In case of mechanic parameters, we test such parameters like elastic moduli, Young, bulk, and shear modules. And in case of thermal measurements, thermal conductivity was this parameter which we are interested in. We also did mineralogical analysis using XRD method. And here you can find the names of all our teams which was involved in our laboratory measurement using AGH laboratory. This laboratory is in Krakow. You can find this there. First of all, we carried out pore space analysis. Here you can find the equipment we used to for this porosimetry analysis. And after that, we prepare our core samples for mechanical and thermal analysis. This is our HH laboratory and our equipment which was used to this analysis. As I mentioned, total on 42 core samples from Polish location were collected. In this core samples we find 14 sandstones, 8 conglomerates, and 20 extrusive rocks. And it's the results are interesting for us because we can compare three different types of rock, sandstone, conglomerates, and extrusive. In Norway case, we collect 10 samples, and this samples was mostly sandstones. But in this case, we can analyze three different formations. Sorry. It's Are formation, Skagerrak formation, and Ula formations. And I would like to show you the result very quickly. I just say new information. We are preparing the publication. This result So I welcome you to finding. In case of porosity result, we found that the study sample is dominated by nanopores and usually reveal unimodal and homogeneous character in the presence of narrow microfractures. The sandstone samples additionally reveal significant pore systems in the range of micro and mesopores, and the frequency heterogony character of pore space. The effusive rock samples show that the widest range of effective porosity. This porosity value from 2% to 12%. And in this case, permeability values calculated are the lowest in case of effusive rock. In case of sandstone samples, the effective porosity is the lowest, differ from 3 and 0.5 to 9.1. So we can also compare the result between different lithological types. We also analyze results from analysis core samples collected in Norway. For these samples, we can find the samples taken from shallower part. Pore space is dominated by the micro and mesopores and has a relatively homogeneous structure. And samples from the deeper part are rather heterogenic with inconsistent and multimodal character of the pore space. We also can compare different information, and we can find correlation between porosity and permeability. You can see here this correlation between porosity and permeability measurements for Norway rock samples. Here you can find results from NMR measurements. It was also possible to compare petrophysical parameters measured by previous method and this method. And it was also interesting for us in comparison of the method. We find that in some cases we find some differences between them. But in this case we also find parameter of porosity as well as we can find types of pore diameters. And of course, in case of enhanced geothermal system, thermal parameters are very important. We did some analysis of thermal properties. We measure thermal conductivity. This is the methods how our colleague did it. You can find it. For each sample, the measurements were performed 6 times. In the first step, the samples were dried and measurements were made at the 4 different temperatures. You can find the temperatures here. The samples were then fully saturated with distilled water, and the measurement at the in-situ temperature were performed. After that, the samples were dried and then fully saturated with the mixture of water and carbon dioxide. The samples were measured at the in-situ temperature. In-situ temperature for the samples was in a range from 109.74 to 124.62 Celsius degree. So the parameters and types of measurements performed is visible on this table here. And the results, you can see the line graph thermal conductivity change for individual samples in different measurement states. The highest average value were obtained for sandstone sample. The greatest variability of the measured value was also observed for the sandstone sample. Anyway, the lowest value were obtained for the conglomerate sample. But the effusive rock sample were characterized by lower value differentiation and a relatively high lambda value. Here you can see the well logging data with the information with temperature and changing the geophysical logs, as well as results from thermal conductivity analysis. In case of analysis of mineralogical composition of rocks, we use XRD method, and the effects show that the main component of sandstones are of course quartz, and we have detailed information about mineralogical composition of our samples. And at the end, we also did mechanical analysis. Several compression pressures were applied for each sample. PNC wave velocity were measured for each compression pressure, and we measure such parameters like elastic module Young, bulk, and shear modules. And universal geomechanical test was carried out for the different compression pressures. And here you can find some results from geomechanical tests. All samples reveal correct behavior between the PNC wave velocities as well as with the elastic moduli. The highest value of elastic parameters were observed for extrusive rocks. But the most varied value were observed for Norwegian samples. And here you can find the histogram of Young module, as well as shear module for different lithological groups. And we prepare some correlation between porosity and permeability of our rocks. We use the diagram when we can find what kind of samples we have. And we also compare these samples to samples taken from Górniczo-Hutnicza area to these parameters. And we found that all our rocks are like EGS petrogeothermal rocks. So we have porosity between 0 and 15%, as well permeability not so high. Just one sample is classified as like EGS hydrothermal, but we are wondering it could be also some test mistakes or something like that, because it's just one parameter. This rock is sandstones, and you can find this blue one is sandstones, gray one are extrusives, and the yellow one are conglomerates. So extrusives are characterized by the lower permeability, as you see, and sandstone are characterized by the high permeability, but almost all of the rocks are classified like EGS petrogeothermal and are very similar to reservoir rocks from Górniczo-Hutnicza area. And our results show that we can thinking about build this enhanced geothermal system, but we also know that very important parameter is our temperature. And our samples were collected from depth not so deep. It was depth about 3,000 kilometers. So the temperature on this depth is not so high enough to build such system. So we decided finally that our reservoir rock will be connected with volcanic rock, which are lying on the depth about 4,200 and 4,300 meters, because the temperature is high. The temperature here is near 145 and 150 Celsius degree, and it should be enough. Of course, the high temperature is better but we really try to model our system with such parameters. We'll see and waiting for these results. And to sum up our laboratory test, I can see that we analyzed 52 core samples. 42 core samples were taken from Polish reservoir, and 10 core samples were collected in Norway. Different range as well as different lithological type of rocks were analyzed, and laboratory tests of rock were performed, including pore space investigation using the mercury injection capillary pressure method, as well the pore space saturation measurement by the nuclear magnetic resonance method, measurements of the thermal conductivity coefficients, as well as measurements of mechanical properties of rock. And the results indicate that the study the rock have suitable parameter as potential geothermal reservoir for CO2 EGS. And these parameters are similar to these parameters of reservoir rock which are in Górniczo-Hutnicza area. So the results of our measurement have been forwarded for further work package for geological modeling and mathematical modeling of the system. So we are waiting for the result. And then I would like to thank all AGH team which was involved in the measurement. So thanks them we finished this work part. Thank you very much.
Good afternoon. My name is Maciej Szmanek. I'm a PhD student at AGH University of Science and Technology, and I'm going to show you a presentation about work package 3, experimental determination of properties and behavior of CO2 EGS working fluids. Work package 3 is carried in SINTEF. And I had a great opportunity to have a 6-month internship in Norway. So I will present some theoretical knowledge and the experience I gained in SINTEF. Here's the plan for my presentation. So let's start with theoretical analysis of expected phase behavior of CO2. It is worth to notice that fluid properties of CO2-rich fluids depend strongly on pressure and temperature. This is true for all properties, and it could have a particularly large consequences of phase equilibrium, where a second phase could lead to breakdown of rotating elements, or in case of water, also serious corrosion. Here is the chart plotted for phase equilibrium for CO2 and water at isotherm of 50 degrees. You can see that solubility of water at all relevant pressure is very low, and it is less than 1%. For a mixture of 5% water in CO2, the saturated pressure depends very much on temperature, and the consequence could, for instance, be that CO2 absorbs water in the reservoir, which could condense to the second phase, that heat is extracted from the fluid on the top side of the process. And knowing where exactly these curves are located for other mixtures is very interesting. Here we have the two charts for phase equilibria of water and CO2 at the critical point of pure CO2 and at 200 degrees. And we see that the solubility of water is really low, but here it's around 10%. So the composition is really important at the temperature. Yeah. What is the current data situation? Significant amount of yearly data were found for CO2 and water binary mixture, but almost all data are from solubility measurements of CO2 and in water at low pressures. And we want to measure the VLE at higher pressures, up to 100 megapascals. And we want to have bigger density in this area, but also in this area higher than 60 megapascals. So there's some large knowledge gaps of thermodynamic properties for CO2 and extract relevant impurities for CO2 of EnerGizerS systems. In EnerGizerS, the specially designed facility is flowing. It is a high pressure and complex phase equilibrium facility. It's employing an analytical isothermal technique to measure phase equilibria. In other words, a mixture which accurate total composition may not be known, but in our case it is known because we prepared 4 mixtures. It's brought into a cell with carefully controlled temperature and pressure because the cell is submerged in a calibration bath in hot oil, so we can control the temperature and we can control the volume and the pressure using bellows. When phase equilibrium is reached, the fluid phases present in the cell are sampled from the GC. And let's start with my work. I started with temperature calibration. We wanted to use 2 SPRT sensors, but during the calibration, unfortunately, one sensor broke, so we had to replace it with PT100. It has a less accuracy, 12 millikelvins against 1 millikelvin, but it's still a good accuracy for our project. How it works, how this sensor measures the temperature. They are connected to the thermometry bridge and the current flows via wires. And we can measure the resistance, and we can divide it into a resistance of special resistance box. We have the ratio, and using formulas, I forgot the English word. We can check the temperature, yeah. For calibration, the ITS-19 is recommended. It is International Temperature Scale of 1990s. It is the standard for the calibration. And for EnerGizerS, the sub-range of from 0 to 231 degrees is recommended. For this case, we have to calibrate in 3 fixed points: the freezing point of tin, freezing point of indium, and the triple point of water. We use the fixed point cell with high purity metal sample. And what means high purity? It is the rule of 6 nines, which is the purity of the metal is 99.9999%. So it is a really pure metal sample. The fixed point cell is submerged in hot oil, and when the liquid sample changes to solid sample, we have the freezing. So we want to measure the temperature at stable freezing state. This is the oil bath where fixed point cell is submerged. We use the stirrer to have the same temperature at exactly at every single cubic centimeter of the oil bath. And HSE rules are very important, health, safety and environment. Silicon oil has these properties that formaldehyd's are formed when temperature of silicon oil is greater than 150 degrees. So you have to be very careful. So the breathing mask with fresh air supply, hazardous material suit and safety gloves are required. Here is the screenshot from logging program and the not stable freezing point. We are looking for the plateau. And the plateau is this state. We have the very, very stable freezing temperature. And you can ask what these jumps are. This is the jumps of the current, because here the current that was flown, it was 0.5 milliampere, here was 1 milliampere, and here 1.31 milliampere. And we want to avoid self-heating, so we have to, after the calibration, we have to extrapolate it to 0 milliampere to have the proper temperature, to read the proper temperature. For water, for the triple point of water, we use other cell, which is made of glass, and we submerge it into a devar with ice. Inside the cell, we have the water in vapor state and liquid state. And to have a solid state, we have to circulate the cold ethanol around -10 degrees to have 3 states in one cell. And after measuring the freezing point of tin and helium and the triple point of water, we can create a deviation function to get to know the proper temperatures that we want to measure after during the experiment. Also, we have to calibrate the pressure sensors. So the HVCP facility has 6 sensors from 10 to 1000 bar. And we have to calibrate it, we have to compare it to a deadweight tester. So it is a device that you placed plates with very low mass, because it is the mass is 30 feet. Then we can mount a special cell, and then we can mount a tube which is connected to the pressure array, and we get some digits, and with these digits we can compare it to the pressure that is read on the pressure sensors. We can compare it, and we can create also a calibration function with a difference different pressure. So here's the example for pressure sensor for 30 bar and for 500 bar. And why we want to have a calibration function? Because for this case, we have only set for 200 bars, and we want to extrapolate it to 500 bars. So this calibration, this function, using this function, we can assess the deviation in the pressure readings. We prepared 4 mixtures, 2% of CO2, 7%, 70, and 99.5. We had a plan to prepare 5 mixtures, but unfortunately we had a CO2 leakage in weighing chamber, so we had to postpone this 5 mixture. But I hope that Syntef will prepare it later. For this case, we used a specially designed railway scale system, where 2 gas bottles are allocated. We use also the OIML weights to compare the difference in mass, because firstly we inject the water, we add the water into the calibration gas bottle. We measure the mass of the water that we added. We compare it to the reference gas bottle, and the difference between the calibration gas bottle and the reference gas bottle should be as small as possible. So if we added water to calibration gas bottle, you should also add some mass to the reference gas bottle. So for this case, we use the weights. And after that, via charging tube, we add CO2. And for GC calibration, it is really important to have a uniform mixture. So a specially designed rolling heating system is used. Here is the gas calibration gas bottle. The rollers starts, they are rolling. And we have to put the lid on it, and we hit it. This is the heating plate. So rolling and heating is for evaporating the water and to reach the uniform mixture. And tubes, valves, and other parts must be heated to avoid potential condensation of water. It is really important to have the uniform mixture without any water that can condense. And here is the output of from the GC, and for the mixture of 70% of CO2, we have a very stable results. So for this mixture, everything is okay. The settings of the GC are very well adjusted, but for the 7% of CO2, the results are very different, from 95% of water to 80%. So it means that we potentially have condensation in the system, or the GC is not calibrated very well for this mixture. So it is important to have stable results. And we generated first data point. The first measurement points of the facility were dew point measurements of the gas phase at temperature of 24 degrees, and the pressure was around 9 bars. We had very good results. The standard deviation is really low, so it is very promising for the next measurements. And here you can see the image of the cell content through the Sessia window during steering. Here is the gas phase, and here is the liquid phase, CO2 and water. So we have the VLE. And here is the chromatogram of dew point measurements. We have the CO2 peak and water peak, and the area of these peaks, we can assume it is the mole fraction. So for this chromatogram, we have the 2% concentration of water in our mixture. And that's all. Thank you very much. I invite you to follow our website, EnerGizerS edu.pl, to follow the results that will be uploaded in the future.
Gentlemen again. My name is Maciej Miecznik. I'm the only one representing the Mineral and Energy Economy Research Institute of the Polish Academy of Sciences. The rest of the team is from the AGH, University of Science and Technology. I will try to talk briefly about geological modeling and not repeat something that was already said. This work package is divided into 4 tasks, which is a general strategy in making any numerical models in geology, especially in geothermal. First of all, we try to construct the structural models, which is also called distributed parameter model. So we want to know the stratigraphic sections, the lithostratigraphic layout of geological setting. Then we create so-called conceptual model. Conceptual model is a type of model which is like a simple geological sketch where we put all the main features that characterize the geological setting. We also place boundary conditions, main thermal features like temperature distribution. This is our imaginations of the system that will further model numerically. Then, as we have GES system, which involves making artificial fractures, then we in task 4.3 we did numerical modeling of rock fracturing process. It was done by an AGH team. And in the last task that now is ongoing, we implement all this knowledge that we gained in the previous tasks into a production model, where we will, after implementation of the distributed parameters, after implementation of fractures, then we will make some production models with supercritical CO2 as a working fluid. So far, as Anna already said, we did this. First of all, we did a simplified wellbore reservoir analytical model to not wait for results from the complex modeling, but we also wanted to have some first approach to CO2 behavior in reservoir in deep boreholes. Then both structural models for both areas in Poland were created. We also got from the Norwegian Technical University also special maps for the Ore formation, the bathymetry map, because it is offshore system, and also we recently got a permeability model for these fractured zones, and I will briefly talk about this. First of all, I would like to mention that we created, in cooperation with all teams, the analytical model of CO2 behavior in both boreholes and in the reservoir. This one-dimensional 1D model of CO2 flow in the reservoir, and it allows us to estimate the heat losses or heat gains during CO2 injection, and then heat losses and pressure losses during the CO2 extractions. And thanks to we know what is the assumed level of the thermosiphon effect and the enthalpy change in this process. This is from this graph you can observe this thermosiphon effect. This is the injection wellhead, the injection borehole wellhead, and we see that this pressure, because on the x-axis we have pressure, and on the y-axis, on the x-axis the pressure on the injection well. Then on the production well we see the difference, which means that we can keep the circulations ongoing. Then, as Anna already presented, these are some figures from the structure modeling from the, for example, the Gorzów block area, which is around 4.5 kilometers deep. This Ośno IG2 well, which is crossing around many different layers, but which are mostly low porous and low permeability layers. Colleagues from AGH made analysis of geophysical logs, and they did a really good job to build a visualization of this seismic data and borehole data. And thanks to this, we could distributed parameters were modeled and then can implement it. We did some statistical analysis, and we see that the zone which is interesting to us has a really low permeability, which makes these rocks suitable for fracturing, and a relatively low shale content. The same was done for the second area, Górniczo-Hutnicza. The reservoir rocks are very deeper and the temperature is higher, but basically it's the same job done for the second area. What next? The same statistical analysis also reveals very low permeability rocks. And for the Norwegian side, the ore formation, this is rather not typical each year because porosity there is quite high. My microphone is not working. Porosity there is rather quite high permeability too, so it is rather called CPG or CO2 plumb geothermal reservoir, which is rather more like water-based reservoir. And Norwegian partners supplied us with more info about this. What is maybe surprising is that the thermal gradient there is higher than most areas in Poland, almost 40 Celsius degrees per kilometer, which makes this offshore reservoir interesting, at least from the point of view of temperature. We chosen the Gorzów block as the most interesting area for complex geological modeling, and this showcase of the conceptual model. So this like some simple cross sections from on the geological setting, the plane view and the cross sectional view. So we can see that from the top view we do two parallel wells parallel to each other around the same depth, and then we can create fractures. They both cross the same fracture zone, and the flow is between them. One of them is production well, then is the injection well, and the whole exchange of fluid is between them, between the horizontal sections. And for this, colleagues from AGH did numerical modeling of the fracturing process. They did several. They analyzed several standards with horizontal well. First, they applied 1,000 meter horizontal section, then 600 meter horizontal sections, and two deviated wells. These deviated wells also have around 600 meters long this let's say, almost horizontal section. And there were different case studies. As I said, horizontal well 600 meters, horizontal well 1000 meters, and both cases were deviated wells. And what they did, they analyzed, first of all, for each case, for each type of the well, they analyzed injection of different volumes of either water or CO2. For each case, it was 5,000 meters of water, 7,000 meters of water, and 5,000 meters of supercritical CO2. And what appeared from the result that the deviated well, we injected 7,000 cubic meters of water as a treatment fluid, provided the best result in the permeability enhancement. This plot just presents some mixed results showing how the width of aperture of fractures it looks like for different cases of the deviated well number 2. So the width of these fractures is very low. It's like from 0.5 to 5 millimeters. So it's very, very narrow fractures, but very permeable. However, this C2 case provided the best results. The fractures are narrow, let's say 1.5 to 2 millimeters, but still they're very, very permeable. And this shows us this view of the deviated well and permeability in that well. And we see that if we compare it to the intact rock that was not fractured, that we see that the permeability enhancement is like 10 billion times. But the fractures are, of course, very narrow. So we need to make a weighted, let's call it a weighted average, but it's more complex in fact, about this permeability enhancement with regard to the intact rock. So, but the flow, however, the flow will be perpendicular to the line, which is the line of the well, because this is perpendicular to the minimal rock stress, minimal principal stress. And comparing different scenarios, we see that the stimulated reservoir volume was the highest in the C2 case. It's about 0.1 cubic kilometer. So this volume, 0.1 cubic kilometers, is the enhanced permeability zone, and this should be enough to drill another well which crosses this section. Let's say this injection well, then a production well should be drilled to cross this zone of enhanced permeability, and then it should be enough to sustain the fluid flow. And to conclude this presentation, I will maybe focus only on this hydraulic fracturing process. So these results, the conclusion from this modeling is that deviated well with a curvature parallel to lithological layering provide the best results. Horizontal sections longer than 600 meters are not effective in that case for that geological setting with that principal stress. Injecting of 7,000 cubic meter water should bring satisfactory results, and injecting more water is not necessary, will not provide bigger volumes of enhanced permeability, but may cause some other technical problems. And there's of course also a strong anisotropy of permeability along perpendicular and parallel axes, which are connected to the minimal principal stress in the rock formation. Now we are working on adopting these fracture models into the production models. The main challenges are adopting the very fine grid in this fracturing model, because the grid is very fine, to a more general grid of a bigger area. So when you need to adapt one model into another, and we need to decide about the size of the computation logs. We need to take into account the precision of the calculation in the project block, numerical stability, and so on. This is in the front of us. Thank you very much that you stayed with us till now. And if any of you has any questions, I welcome you to ask me.
Hello everyone, my name is Paweł Gładys. I'm working at the AGH University of Science and Technology, and today I will have actually two presentations on the EnerGizerS project. The first one is devoted to the mathematical modeling of CO2-based topside system for heat and power production that is led by the Syntef Energy and in person by Trond Andersen, who could not be with us today live, but he's joining us, of course, online. So going to the presentation, I will just quickly say a few words about what is the topside system of the CO2 EGS. We're basically talking about a turbine and a cooler that allows to utilize the high pressure and high temperature coming from the production well and then put it back with a lower pressure and lower temperature. The purpose of this whole topside system is the efficient exploitation and conversion of extracted geothermal energy. So the hot dry rocks that gives the heat to the working fluid, which in our case is supercritical carbon dioxide, is the key point here to utilize it in the most effective manner. We are analyzing the cycles that are focused on power only or heat and power production. And of course, we are fully aware of the fact that the topside operation impacts in a way the thermal conditions over time. So we will be dealing with the temperature degradation. So the temperature and pressure at the point of the production well will decrease over time within the long-term exploitation of the reservoir. We just basically cool it down a little bit. And so the goal is to evaluate the topside system design and performance for selected case studies in Poland and Norway. There will be 2 in Poland, 2 in Norway. And Syntef is focusing on the Norwegian scenario when AGH and Exergon, the private-owned company that is also associated with our project, will be more focusing on the Polish conditions. And also taking into account the opportunity that it gives us that we are all working with different process modeling tools, we will also would like to compare the different approach in terms of process modeling of such systems. As mentioned before, we will be analyzing 4 scenarios, 2 in Norway and 2 in Poland. The ones in Norway are all located offshore at the subsea installation. So we are actually talking about setting up the installation on the bottom of the sea in order to avoid the decrease of the temperature when we want to take it to the platform. On the other hand, we are also thinking about the platforms here could be a great source for supplementing the carbon dioxide to the system. As we already mentioned, that part of the carbon dioxide will actually be sequestrated. In terms of Polish condition, 2 locations, 2 geological formations are considered, the Gorzów Block and the Mogilno Szprot. And we also analyzed them from the point of view, not only the geological conditions, of course, this was the main reason, but we're also looking at the possibility of trying to utilize the excess heat to be integrated in the district heating system, or in a case, is there also an availability of the CO2 sources at the required capacity. So putting this all together, it gives us these 4 scenarios that will be analyzed in detail through the rest of the project with a specific pre-feasibility studies, including also economic ones. Our Polish are mainly focusing on trying to use the heat in the district heating system, wherein, of course, in Norway case, on the subsea, on the offshore location, there's lack of heat demand and power generation only. The type of energy cycles varies from direct supercritical CO2 cycles through hybrid ones, as well as indirect ones with the organic ranking cycles as well. So first, I will just start with the 2 basic concepts of utilizing the excess heat that we get from the EGS system. First of all is the 2-stage expansion and heat export. So there is a possibility to export part of the heat into the district heating system. So we're talking about the cogeneration, but we can of course operate it without this. And we are dealing with a direct supercritical CO2 turbine, then a mixer which gets the CO2 makeup flow, and then of course the gas cooler and the injection well, and then we close the cycle. On the hybrid ones, we are talking about the option of taking this heat available and utilize it within the organic ranking cycle at different designs. But we're of course also, first of all, utilizing the potential in terms of pressure difference and temperature in the direct supercritical CO2 turbine. When we're looking at the Norwegian scenario, we're talking about the offshore only case, as this is the only place where the actual favorable geological conditions for EGS system can be found. And here are some of the parameters, but first of all, let's take a look at the depth. We're talking about 4,700 meters below the sea level. So we're talking about a significant depth in order to get to the EGS system suitable for the operation. But the temperature is quite promising, around 160 Celsius degrees of the reservoir temperature at that depth. Topside and reservoir interactions are part also of our investigations, as we are not only focusing on the case studies itself, but we're also trying to develop and work on the process modeling. In these terms, we also acknowledge that there is a strong interaction between injection and extraction, and we would like to have a comprehensive model, maybe not as detailed as my colleague in the previous presentation said, as very specific one, but trying to get as good representation as possible in order to also try to see how we will over time influence this with our operation of the topside system. And so we also decided to extend the topside system and include the simplified well and reservoir model that was already mentioned. And in order to do it, we analyze it, and with modeling methods, of course, we have the topside system, the turbines, pump, heat exchangers, mixers, and of course, the thermodynamic models are different from depending on the type of machinery or equipment, isotropic efficiency for turbines and pumps, and for example, pinch point temperature difference for heat exchangers. On the other hand, we're talking about the model for the geothermal side. So we're talking about everything that happens underground, under the surface. And of course, the model was already described by a colleague. In some of the cases, in some of our modeling approach with different tools, for example, Syntev is using their own modeling code. So that's why they incorporated everything at once. Our colleagues that worked with Hexagon are working with Thermoflex software for process modeling. So they, for example, also in a way incorporated this model into their tool. In IPSE Pro, we also did something similar. So the general idea is to have everything in one process model in order to be able to not only simulate, but also to run the optimization problems. So for example, the optimization can be to maximize the net total power, which is the power available from the CO2 turbine and the ORC turbine minus all the power consumption, mainly in pumps. The variables would be, the variables would be, for example, the CO2 injection pressure, mass flow rate, temperature, or for example, the high side pressure of the organic ramping cycle. There are, of course, certain constraints like minimum temperature difference in heat exchangers. Our colleagues in Syntev used gradient-based constraint optimization method, and the entire system is solved as a single mathematical problem. So we can simultaneously optimize both the operational parameters as well as the design parameters, for example, on the subsurface side. When we are looking at the well and reservoir calculation, my colleague already also mentioned that we are working with the added value of the pressure difference. So we basically have a thermosiphon effect in which we first of all utilize for the purpose of trying to not be forced to add additional pump before the injection well, which also on both sides allows us to avoid an expenditure in terms of investment cost, but also allows us to get a better efficiency, overall efficiency, which we also try to check before. So basically, we can see here on this graph where the points are, depending on where we are with the injection and production well, as well as the reservoir, on this temperature and pressure graph. So now we have the pressure loss associated with going through the reservoir, so the friction, and then of course the production well friction and the pressure, static pressure loss. When we're talking about the direct expansion cycle, so a very simplified one without additional heat extraction or without organic ranking cycle, you can see that here are the results of the scale parameters presented here and the injection mass flow rate for a specific location in Norway. And we can see that at some point we can actually get an optimal value of the net power depending on the injection mass flow rate, which means that for a specific design, for a specific borehole, for a specific EGS system, there is an optimum from the power point, the net power production point of view. We can of course try to analyze it not from the point of view of mass flow, but for example the diameters of the wells, and we can also see that there is also a relation that with the increase of the diameters within the analyzed range, the net power increased for a fixed value of the flow rate. And so when we look at the system optimization results from the Norwegian case, just comparing those two options, so the direct expansion, direct supercritical CO2 cycle, and the hybrid one, the organic ranking cycle, we can see that of course in hybrid cycle we will get additional one, or maybe not less, a little bit less than 1 megawatt of electrical output, which of course could be of great value from the point of view of economic assessment. But the lowest possible injection temperature is always selected. The higher density in the injection well increased the wellhead pressure difference. So this is also what my colleagues were already talking, and there was also an answer to why we are trying to investigate a supercritical CO2 in such a systems. Here you can see also the trade-off between the wellhead pressure difference and the mass flow rate. For the case, the direct one, the blue one, and the hybrid one, the red one, you can see that the difference aren't that big, but they actually are significant in terms of final and efficiency of the compared systems. And I would also like to say that this is not only the ones, the cases that we were investigating. We actually look at a much wider range of designs that we investigated. We investigated the ones that we actually, for example, don't have the supercritical CO2 cycle, but we are just merging it with organic ranking cycle without the actual turbine, assuming, for example, that the technology is not there yet in place, as an example. We also look at the direct CO2 cycles with organic ranking cycle, that the heat extraction is happening not in between the stages of the turbine or at the end of the turbine, but before actually the working fluid enters the turbine, trying to get a higher parameters in the organic ranking cycle. Or the ones, as I mentioned before, that allows us to split the turbines and have the cogeneration system, and also try to vary the parameters of temperature here in order to meet the requirements for different generation of district heating systems, right? We're talking about third generation, which is mostly common in Poland, but we're also looking for fourth generation with much lower temperature requirements. And so also here a study this time for Polish conditions. And as you can see, depending on the case, we can also in some of them find an optimal value again of the mass flow rate in terms of the net power produced in such a case, which is a promising idea that when hopefully we will move to a more detailed process modeling, to the mathematical modeling of the reservoir, we can start around this value of mass flow and trying to figure out the strategy for the long-term operation, taking into account that here we can actually get the maximum outputs in this specific designs. Here is also the same graph, but shows the unitary net power output in the value of kilowatts per kilograms per second of actual mass flow. And you can see that there are those curves showing the optimal value. The only this is only not visible in the indirect one where we actually don't have the supercritical CO2 turbine. So the outcomes of our work package and the outcomes of the project in terms of process modeling will be definitely a process modeling framework with which we try to get as detailed information as possible, and also to give us certain guidelines for the future references in terms of how the process modeling of such cases should be done. We are mainly in the specific assumption ranges for variable parameters. We are also trying to investigate the most optimal operational strategy from the topside point of view. Right now, we are on the point where we are looking more at the energy efficiency point of view, at the net power output, but we will definitely look at this from the economic point of view. We are developing several universal simulation models for such systems in different softwares, and then the final goal is to have the case studies, detailed simulation and optimization models ready. The thing that I mentioned at the beginning, the reservoir degradation, is something definitely that we would like to include also in our simplified model and try to get it as far as possible with using only one tool. Definitely the conditions will change in the reservoir and wells over time. First of all, the thermal degradation of the reservoir, but also we have to be aware of the fact that the more CO2 will be stored over time, it also will affect the reservoir itself, or for example, its capacity to sequestrate additional volumes of carbon dioxide over time. And so we will definitely work on this in terms of work package 4. And we're also looking forward to trying to use the idea of exergy and exergy efficiency, trying to figure out how we can nicely implement it and try to find its application in such a system. We of course did the net exergy efficiency of the whole systems, depending, for example, from the injection mass flow rate and the injection temperature. We can see that we get the optimums again at the lowest temperature and the values of mass flow rates around 100 kilograms per second. Those are again results for Poland, Polish condition, and Kutno trout. But in general, we are thinking about trying to introduce the exergy efficiency and exergy analysis in a more organized manner, also to the process modeling and assessment. And so the overall goal is to provide recommendation for topside system configuration and input for the techno-economic studies. As I mentioned before, we are very excited about comparing the modeling approaches, basically in 3 different institutions, including the one that is working basically on commercial basis as the Hexagon company. We also would like to extend the system models with more realistic components model and behavior where needed. Taking, for example, the great opportunity that gives us the chance to working with Syntem Energy and working with their own modeling code. And the main thing is the overall EGS performance over the long lifetime, depending on the operational strategy. So this is something that is definitely there for us in the future. Thank you very much. And as mentioned before, I have 2 presentations. But the second one will be very short. As already Professor Sowicza mentioned, we are just starting the economic assessment. And so I was also asked to give a very short presentation on behalf of the team that is, I can say right now, is involved in this work package, to say a few words about the techno-economic and environmental assessment of the systems. And basically, as I mentioned before, we will be focusing on the economic and pre-feasibility studies and environmental impact assessment for those 4 cases. But we're also going to take a look in one of the tasks at the regulatory and policy framework analysis. And again, we would like to share with the community, the scientific community, the general assessment framework for such systems. We have several milestones and deliverables. I would like to just point out to this first one, which is what I mentioned before, the guidelines for techno-economic and environmental assessment. This, we hope, will be an added value to the scientific community in terms of how to assess such and novel systems in an organized manner. We are at the beginning of our work, so most of the things are still ahead of us. But somewhere before the end of the project, the guidelines should be available, and hopefully will also be reviewed in a way by the scientific community to be able to improve them if needed. How we divided the work? Well, of course, again, System Energy is providing the Norwegian perspective, and the AGH and Hexagon are providing the Polish perspective. Hexagon, as this is also part of their daily work, they will conduct the techno-economic assessment pathway. AGH University will focus on the environmental assessment pathway, including life cycle assessment of such systems. And also our colleague from AGH will work on the safety, regulatory and policy assessment pathway, trying to figure out what kind of legislation needs to be changed, what kind of risk we are talking about in terms of operating such a system, especially on land in the locations like Poland, because I guess in terms of offshore, this is a little bit less risky. So this is what I meant. The storage safety and the legal and regulatory perspective is also part of the work package, and I hope it will also bring a new insight into what are the non-technical barriers for implementing such a systems. We will, in terms of what we will be working with, what kind of methods will be applied in terms of economic assessment, of course, levelized cost of electricity, levelized cost of heat, net present value, internal return, standard economic assessment methods. But we're putting a lot of effort to try to get as good correlations for the investment cost of the specific components. In terms of environmental framework, we are first of all following the ISO guidelines for the life cycle assessment and trying to include the life cycle perspective, and also to assess the avoided greenhouse gas emission, not only from the actual power generation, but from the fact that also part of the CO2 is being sequestrated at the same time, which avoids a sequestration in other locations, maybe a little bit more risky due to the, for example, depth of the storage. In terms of safety, storage safety, the minimum safety conditions should be assessed, and as I mentioned, the regulatory and policy framework, the barriers and opportunities identification is the point here. We are of course not starting with anything. We have some results from our previous projects in terms of, for example, assessing different methods for calculating the cost of the wells or the machinery in the supercritical CO2 cycle. So different methods were assessed, trying to combine which one could be actually more suitable for our applications. We did also the studies regarding the levelized cost of electricity depending on the enhanced geothermal system zone permeability, so how well we will fracture the zone, or for example the mass flow rates, independence on the net power or the values here. I would just like to point out that at some point we are actually able to get to a quite nice and still acceptable, I would say, especially today, levelized cost of electricity. Couple of years ago, 2 years ago, 3 years ago, 200 euros per megawatt hour seems extremely high. Right now, we are actually more close to it on the regular basis. And so this is all in terms of work package 6. Thank you very much.
We finish our presentation, our technical presentation. Thank you for participating for this session. If you have any question, please you can ask. If do you have any question online?
Just checking. There is something coming, but maybe let's give it a moment.
Okay.
Someone started writing, but it's not.
Okay, so please, if you have any question, you can write to us. I can say that our research is financed to the Norway grant. Our EnerGizerS project, the full name is CO2 enhanced geothermal systems for climate neutral energy supply. Is realized by Polish Norwegian consortium, and today we do not finish our project. We will finish it next year probably. So I would like to invite you to our final event. It will be organized next year in September. So please save the date. Probably between 9 and 21 September. In AGH or Krakow, so I welcome you for this event. And you can also find information about our projects and find results from our project on our websites. You can find the address here, EnerGizerS.edu.pl. So if you have any questions, please contact us. And I hope that it was interesting for you, our session. So thank you very much. This is contact to me. You can use it. Thank you.